Thanks so much for joining me this afternoon. I'm Tim Wagner. I work for Amazon Web Services. And we're chatting today about kind of this new industry-shaping idea called serverless. So I'll give you a little bit about my impressions on that, and we'll talk a little bit about that, how that kind of manifests within the products and services that we work on. But I kind of want to start by taking a little step back in time. So it's 1950, and punch cards are all the rage. There are companies that do punch cards. There are open standards around punch cards. Punch cards are how you do DevOps. They are the way that you transmit code, data, and configuration to computers. They are the deployment technology of choice, the best practice around, as it were. So there's this interesting question, all right? And so I'm about to say something provocative here. But DevOps today, these are our punch cards. These are the punch cards in 2016. Because they're about a point-in-time artifact, getting code and information onto fleets of computers, particularly, though not necessarily only, in the public cloud, that make them do what they're supposed to do. And they are ultimately an annoyance. They are about solving questions and answering questions that ideally we could let machines and automation do for us. Like, have we patched that machine? Do we have the right set of things running together in the right places? Do we have the right kind of servers? Did we pick the right type this time around? In fact, did we get enough of those servers? Particularly in the right places in the right data centers for the right kinds of things that we need to do. So on and on and on. All of these questions that we're forced to ask and answer and worry about and automate and work on each and every day. So put that on hold for a second. Let's talk about one other thing. Scalability, reliability, and fault tolerance. These are some of the hardest things to get right. These are the things that, especially perhaps if you come from, let's say, a mobile application or an embedded device software background, might not have been what you've spent the last 10 or 15 or 20 years working on. And you might not even have anybody on your team who's got, say, an advanced degree in distributed systems analysis. And even if you do, you know full well that of all the ways to model software, these are some of the most complicated systems to deal with, right? Even at the theoretical level. Systems that can break, that have partially operating networks, that can transmit some but not necessarily all of their information, right? It gets really difficult to build systems that work well, and then to prove, test, monitor, and analyze those systems in real time. So what if we could achieve some of these ideas without working so hard at it? In fact, what if we could take kind of that ball of complexity that's both this aspect and the business logic and kind of tease those two things apart, which would let some people work on the business logic and then let other folks, say, our cloud providers, deal with some of these other parts for us. So we've all kind of heard this word serverless, right? But if that's the answer, what's the question? And kind of my thesis for you here is that it's the abstraction level for the cloud. It is in fact the right abstraction level to think about deploying, running, monitoring, and basically dealing with code in the cloud, particularly in the public cloud. Now some of you are going, oh, I've heard this before, right? This is just PaaS, right? Like there's this thing that was supposed to solve all our problems. It was going to take that assembly language of the cloud and it was going to lift us all up to this higher level of abstraction. The problem is the P in PaaS, right? That platform was too curated, it was kind of too fat from a framework perspective. And while I think you could go solve those problems, I think you could go fix them on different platforms, the real problem with PaaS, as kind of an answer to sort of serverless, is that it was sort of last generation's idea. It was about deploying monolithic applications. We sort of got the nouns wrong, right? And therefore all the verbs are wrong too. Because it's about deploying and monitoring and dealing with servers. The platform there is kind of keeping those servers alive. And ultimately, servers are the wrong unit of abstraction to make serverless really work. Instead, we have to go to this smaller level of granularity. And whatever you choose to call it, microservices, micro-applications, it's really about deploying code and then dealing with that code and scaling that code at the level of individual functions. And I use functions kind of generically here. They could be methods, depend on the binding to a particular programming language. But a granularity that matches up to an individual request and an individual unit of work that we're happy to scale at. Because when you go down to that level, all sorts of really interesting things become possible. That complexity of scale and fault tolerance, as we'll talk about here, is something we can start to factor out. When that's bound into a monolithic application, it's virtually impossible to factor it all out. So I spent some time thinking about, and kind of in the spirit of Agile, what should the serverless manifesto be? And I want to kind of take a little bit of time to step through this, because it kind of as a definitional sort of moment as we're beginning this journey here, I think it's important to talk a little bit about what do we mean by serverless. So first and foremost is what I just said, that functions, not applications, become this unit of deployment and scaling. That's probably the single most definitionally important element of it. And then kind of following right on the heels of that we don't have machines, real or virtual, or even containers visible in the programming model. Because all of those things are about abstracting either hardware or operating systems. And if we're going to be truly serverless, and yes, that also means truly containerless, then we need to think about the level of code and functions instead, not the things on which they run. Because otherwise we'll end up scaling those rather than our code. Permanent storage lives elsewhere. And this doesn't mean that you don't have main memory or some ephemeral disk, but it does mean that you permanently divide these two abstractions. And that's important for lots of reasons, not least of which is that you get to pick different providers for those two parts of your equation. It also forms a firm contractual boundary there that means you aren't accidentally getting state locked onto a container or a machine. And then we kind of get to the heart of what happens when you do this. Scaling by request, and it's got such an important corollary, I stuck it right in there, right, which is that users can't over or under provision. You actually take away, by definition, the ability to get that wrong. Can't see the machine, can't have the wrong number of machines. Can't see a container, can't have gotten the wrong number of containers. And then there's sort of an economic pivot to that, which is you don't pay for those things unnecessarily. Because you can't have too many, you can't pay for idle, because they can't be cold. Similarly, you get fault tolerance because you don't have this tight affinity, and especially the fact that the storage is separate means something goes wrong, we can just run it on a different machine. Bring your own code, so none of this, I'll decide what libraries are right for you, you decide which libraries are right for you, and then metrics and logging and other kinds of infrastructure that are kind of built in as a universality. So that list, perhaps unsurprisingly, is what I wrote down back in the day when we were first getting going on AWS Lambda, right? That was the list of product requirements and experiences that I set out, when we first formed our team to build the Lambda service. So to no particular surprise, that's how Lambda works today. And so that's a good description actually of what you get out of it as a service. And then what you can do with it is quickly bring code into the cloud, including your own code, including native code, and you can create things like mobile backends, event handlers, data processing systems. And we'll take a look here in a little bit at some of those design patterns and what you can do with them specifically. Now, one other thing I want to mention sort of before we leave this is this final point here about running code in parallel. Because what's really nice about serverless systems, like, yes, they speed your time to market. Yes, they mean you don't have to recreate the wheel, which is great. But one of the things they do is they turn complicated distributed systems coding or parallel coding inside the language into simple horizontal scale that your provider, your cloud provider in this case, is giving you. And that's really nice. Because I don't know what kind of teams you work on, but typically I found in my career that you have like the one or two guys who really do the hardcore parallel or distributed systems, right? And you give them that work to do. The nice thing about this is it democratizes it. You can take a little bit of Python code. You may never have written a highly distributed system before. Maybe you're an embedded systems developer or you specialize in mobile client. And now you can create something in the cloud which can run it at 10,000 or 100,000 TPS. All right, so let's talk about that. How do you build these apps? Well, maybe the easiest thing to say is what you shouldn't do, right? We don't make them monolithic anymore. We express functionality not as a large-scale application, but as this collection of independent functions, right? And then we put APIs where we need those abstraction boundaries. So we still have a classic interface versus implementation divide. And then you leave out the boring stuff. Now that includes things like metrics and logging, which, actually end up being kind of complicated when you do them at a per request level at scale. But most importantly, the web server and the API hosting bits. And there are kind of two reasons for this. Like one, you don't want to replicate that into every app because that kind of slows you down. It's a lot of unnecessary duplication. But the more important fundamental part of that is that if you need to have that in the infrastructure now so that the system can see your requests. Because if the function and the request is going to be the unit of scale, the system has to be able to see that and help with it in order for all of this to work. And then as we mentioned, you kind of get to skip some of these hard parts. These distributed algorithm pieces that are all about things like fault tolerance and scaling that have nothing to do with the actual business logic that you're trying to get running. And so what they do look like is these individual functions, sometimes with HTTP endpoints. Often they're asynchronous, which gives you that temporal abstraction and division in the same way that APIs give you the sort of contractual distinction at the code level. And they're not necessarily simple. So the application, the scaling and parallelism part, that we want to make very simple, but the code, the algorithm, that will vary tremendously. And on Lambda, since I have the privilege of seeing all of these customers who are using the system, I see people who bring as little as a single line of Python code and they turn that into a robust, fault-tolerant, scalable algorithm. And I see people who bring millions of lines of low-level C++, image analysis or video analysis code, and they run that as a service as well. So the algorithms span a huge, huge continuum here. So it's not the case this is just lightweight choreography kinds of coding. It's really a broad spectrum. And we see people doing billions of object manipulations with S3. We see people doing an incredible amount of data processing. And of course, to be honest, that's why this is economically viable as a service, not for lightweight choreography, but for very heavyweight computing needs. So usually about this time, somebody always pipes up and says, but wait, I've got this thing and it's really, really important that it run on big iron. I've got to have the big server. How do I deal with that? So this is my kind of how do you run a 1 hour task. Let's say you've got something, it takes a whole hour to compute. So the old school way, you go get yourself a machine. You stand it up, you deploy all your software, you run it for an hour, which is great until the day the machine dies or there's an error and you've got to restart. Now 1 hour turns into 2 hours, and that's assuming you can kind of get it running again right away. And then even worse, what if it really only took 15 minutes? Because you wouldn't keep a machine for an hour if you needed 59 minutes and 59 seconds, right? You'd need more. And so you're probably wasting some of that, and that's not so great. And then we'd have the whole pets versus cattle debate. So the new school version of this, do 61-minute jobs instead. Break your work up. And we've seen people take videos apart, files apart. There's almost always a natural kind of scatter-gather paradigm, for any particular application domain of choice. Now who cares if a machine restarts or you get an intermittent error? You just redo that job. And instead of taking an hour, it takes a minute. Worst case, instead of 2 hours, it takes 2 minutes. And it doesn't matter so much any longer what kind of machines you run on because the performance comes from horizontal scale, from that parallelism, not from making bigger and bigger and bigger choices in the underlying iron. You stop wasting time and money. If it turns out you only needed 15 parallel jobs, that's great. You only run 15 instead of 60. And I call my metaphor for this, the drive-through window, right? I don't want to raise a cow to turn it into hamburgers. I want to run through the drive-through window and get some hamburgers. Now, one of the things we tried really hard not to do, and it's always kind of interesting to see what people keep out of a system, is having some kind of complicated programming model. So on Lambda, for example, and this is, others in the market doing very similar things, you can run code in Java, Python, Node.js 4.3, which we finally got launched. Plus you can bring your own languages. So we're absolutely happy to have people bring their own language runtimes. And one of the reasons that's true is because we don't do anything special with the language runtimes, right? It's just a convenience that we offer some of our own there. Plus you can bring your own libraries and you have full and complete choice over what kind of code you want to run as long as it can be linked in the underlying operating system image, in our case, Amazon Linux. Now, what's nice in there is that the programming model is just the language. There's no special framework, there's no magic to incantation to how it gets invoked, there's no special library you have to have included. We throw in the AWS SDK in some of these languages for convenience, but even that you can override easily enough. And the protocol, if you will, is just HTTPS on the wire and JSON sort of in and out. It's a really simple scheme, which means also that it's a scheme that you don't have to spend a lot of time learning. And because we use stock languages, easy in, easy out, right? There's nothing particularly proprietary about running Java code or Node code. So let's take a little look at what this is like. So first I'm going to show you a little website that we built called SquirrelBin. And what SquirrelBin is just an executable gist hosting site. So I'm going to go ahead and create a little code here. And I'll do sort of just enough to kind of see something execute. So there's my acorn. Save the code. Now I'm going to go ahead and execute it. We can see this run. So what's interesting isn't that I built a little website here. What's interesting is how we built this website. We didn't deploy any servers at all. So let's take a look at what it would be like to actually go create that on Lambda. So this is the Lambda console. I'm going to go ahead and create a new function here. And we've got some blueprints. Blueprints are basically just like getting started templates for code. So I'm going to pick one. That's microservice endpoint. Go ahead and provide a little information here. And you can see some of this code is already filled out for me here. And actually what's interesting about this one, I'm not going to have to change the code as it turns out. Now I'm going to pick a role here, and what I'm doing with this is the moral equivalent now of when you're installing an app on your phone and it says, do you give it these permissions? I'm going to give this one permission to access DynamoDB, which is our NoSQL data store. Then there's a little configuration down here to pick duration and power levels. I'll come back and talk about that a little bit in the rest of the talk, and we don't need VPC for this. So go ahead and click next. It's going to let me verify all my settings. I'm going to click through again. So I have to keep scrolling here, and then go ahead and say create. All right, that's it. I've created my function, and now my function is actually deployed and ready to go. Whether I execute a couple of requests at the next minute to show you folks, or send 50,000 TPS, either way, Lambda's now prepped to run that code at whatever scale I'd like to operate. It's already fault tolerant, production secured, scalable, and backed by a team of developers and systems engineers sitting in Seattle ready to ensure it keeps running. So I'm going to go ahead and test this now. I'm not going to set up the whole Dynamo backend in the interest of time. I'm going to show you one operation that we built in here, which is just a simple ping, just to kind of give you a sense of the code running. So I'm going to change the JSON. This is the JSON that's going to flow in. I'll save that and click test, and we'll scroll down here, see it succeeded. It did in fact say Pong, which is good. It actually did what it was supposed to do. And then I get a little bit of information about the run, such as how long it took, as well as a copy of the logs, which aren't super interesting here. Now, that code that I have on there, as I mentioned, I didn't actually have to change. So let's go back and take a quick look at that. I send it a ping operation, but here's an example of the other operations we could send. So when you saw me create that acorn, this is the code that was running, dynamo.putItem. And that's all that it took. This code is the entirety of the back-end CRUD operation, or if you prefer, the control plane of that SquirrelBin site is all and only the code that's running here. It's just a simple front to Dynamo, and because NoSQL kind of has this nice schemaless quality, I didn't have to go set up a relational database. All of the data shaping, if you will, was handled on the client application. And the client code is being served out of an S3 static website, so once again, there's no server involved in that. In this case, it's a single-page JavaScript app that's kind of doing that work on the client. We could, with a little more work here, have built a heavy server-side app where we'd emit the HTML dynamically. Now, there's one thing I haven't shown you yet here, which is how we actually do the run part. So let's take a quick look at that code. So this is the only code that we actually wrote on the server to make SquirrelBin work. Everything else was done client-side. And kind of unsurprisingly here, at the heart of this is a call to eval. Now, of course, this would have been a little harder in a statically compiled language like Java. And I know what like half of you are thinking now is, uh-oh, he's gonna get fired, right? Because he used eval in this code. And here's where the joy of a sandboxing system comes in, right? Because this code is running eval inside these nice little sandboxes that are providing security and isolation. Plus, what you saw me authorize earlier gave it access only to that Dynamo table. So it can't start rummaging, no matter what kind of code you put up there. It can't begin rummaging through my account here and start doing illicit things to the rest of my AWS resources. So that's it. There's the eval. We saw the kind of the CRUD part of the operation. That's the entirety of the server-side code. I won't bother showing you the client-side piece, but we have a whole blog article on this. You can find it on the AWS Compute blog that actually has all of the client-side setup as well if you'd like to recreate this on your own. All right. So we talked a little bit about the functions. You saw me create a function there. Let's talk a little bit about events. So in what I did here, I send it some JSON, right? Like how does that relate to an event? So events are nothing more than a JSON with a particular schema that happens to be coming from another service. Could be an AWS service or could be some other kind of third party, like perhaps a message from Slack. And we've integrated this with a whole variety of other pieces of our platform. So for instance, if you upload a file to, let's say you upload an image to S3, you can send an event to Lambda, which is just a little JSON parcel, similar to the one you saw me edit, that says, in this bucket, this object changed, at this date, and gives that function enough information to do something about it. For example, to turn an image into a thumbnail. And then we've kind of gone to all the different pieces of the platform and said, where are all the places that a resource changes state, or a lifecycle event happens, or some piece of data flows through a system, like inside a Kinesis with streaming data, where we can define that as an event and send it to Lambda such that we can modify, transform, audit, et cetera, all of those pieces. And that's kind of where we get value out of attaching functions in this serverless way to all the other parts of the platform. So let's take a look at one particular example of how that might work. Let's say that we wanted to build an audit system. And by the way, we only got like 5 minutes to do it. Like sounds impossible, right? It's actually super easy. We go to CloudTrails, which is our API logging, and turn that on with a couple of clicks in the console. That sends events to the CloudWatch Event Hub, which we can then hook up to the Lambda function and write a few lines of code to do auditing. And so with a couple of console clicks and a little bit of code to do some custom filtering, you can get something that'll send you a text message every time somebody in your organization, say, fires up a new EC2 instance. So you can check, because maybe you weren't expecting that to happen, whether they really have the right kind of privileges and roles and you were expecting that after all. So just a simple illustration of the kind of thing that once you hook these events up, you can do with the entire system together. Okay, frameworks bad, services good. Like what's wrong with frameworks? By that I mean proprietary, heavy client or server-side logic that kind of locks you into a particular combination of services. One of the things that you saw in the code here was that we called out to Dynamo, but it's just embedded in code. I could just as easily, or perhaps with a little more SQL schema work, have gone out to something like MySQL through a VPC and done the same example for Squirrel Bin using a relational backend. Or I could have gone to any other provider's publicly hosted data storage solutions if I wanted to. So while, of course, I'm happy if you use the things in AWS, I'm also equally happy if you write your own, including going through private endpoints, because we provide support for VPC, or any place else on the private internet. And here's where building these serverless systems at the level of the language runtime becomes super powerful, because what you're interacting with in this case is Node or Python or Java, not some particular framework that you've got to sort of stick with forever. So let me drill in on a couple of things that you saw there in the demo, either explicitly or implicitly, and explain what was going on. So first, I mentioned that memory size there, and although we accepted the default, we could have changed it if we wanted. What was that all about? So you can think of this as a power level. Rather than coming in at the infrastructure and saying, I want this kind of instance or that kind of instance, we give you this simple dial, and you can turn that kind of all the way down or all the way up. And when you turn it, you're adjusting everything at once. Memory, CPU power, disk I/O, network bandwidth, kind of all of the pieces together. So how do you know how to set this thing? There are a couple of easy answers. You got something that's CPU bound, set it to the highest possible number, because the sooner you get done, the better. and the price scales linearly with the power there, so that one's simple. Might as well get the work done quickly. Got something that's I/O bound, like what we're doing here. You want to set it to a low level because there's no point in paying extra or providing extra power for something that's going to run infrequently. If you have something that's super latency sensitive and where the work is balanced or varying between I/O and CPU bound, that's the hardest case. That's why we put the knob in the first place, so you can tell us what your price performance ratio should look like. And then you can set the duration anywhere from kind of as low as a second all the way up to 5 minutes in time. Now the other thing I want to talk about here a little bit is versioning. So we edited the code there, and we actually kind of went through a blank version into sort of a version that had some stuff in it. What I didn't show you was publishing. And while there are a lot of different pieces of authoring that we could talk about, this one's worth a little bit of discussion. So generally what happens is when you get to something you're happy with, is you do what we call the publish step, which gets an immutable snapshot of that code and assigns a lifetime moniker to it. And by lifetime, I mean really lifetime, like around till the end of time. So that name for a function can never mean anything else. You can delete it, which is your right, but it'll never mean anything else. That makes it really easy to do things like testing, to give out moniker to clients that you know can be stable over time. Now, sometimes you need to be able to modify on the server side what your clients are pointing to. That's where aliases come in. Aliases are just symbolic links. So you get something on the server that can point to any one of those immutable versions, and then you can change which version it points to so that the clients don't have to get recompiled. So one of the questions I get asked occasionally is like, but how do I do like blue-green deployments? Like how do I make Lambda deploy things in the right way? So let's talk about two different things there. First of all, actually deploying the Lambda code on Lambda, like that's something we take care of. In fact, that's kind of part of that serverless manifesto, right? Is that you shouldn't have to see that and you shouldn't know about it. Within a few seconds, like the code that you've uploaded or published should be ready to go in that region or for as many regions as you ask for. On the other hand, you might want to do traffic shaping. That's totally legitimate. Maybe you want to run an A/B test. So what you do there is you just stick another function in front and let it serve as a traffic cop. And that way you can have it send traffic to A, to B. You can change the percentage dynamically, maybe by reading a dynamo table or something else. So you can play all kinds of games all day long with the traffic shaping piece of it. And one of the things that makes that easy is sort of putting an HTTP endpoint in front of it, of course. So API Gateway, which also supports immutable deployments, and then what we call API stages, which let you separate a deployment that's for development versus the one that you ultimately use in production. And kind of one final point here is, sort of almost, I guess, a sort of a call to action is, I love how Docker makes things kind of write once, deploy anywhere. I love how Swagger makes it easy to treat APIs as code that you can version and retain, and we've just added Swagger import to API Gateway last week, which is a really, really nice step forward because I know most of our customers like using that. But what I would love to see in the community is a way to bring these pieces together. Kind of as the guy, sort of the Lambda guy here, like I'd love to with my Lambda hat find a way to put the code and the APIs together. And I don't think we quite yet have the formalism for that. I think that's an interesting area for future work. Okay, so I get this question all the time, so I'm just going to kind of preempt it and chat about it here a little bit now. What is it? Like if you could kind of pull the curtains back, like what's going on here under the covers? Is Lambda just like a Docker with a script on it or something? Like what's going on there? So let's kind of start from the bottom up here. Lambda is using Linux containers, but it's using them as an implementation, not as a programming or deployment abstraction. That's kind of how we differ from things like Docker and the EC2 container service. But under the covers, they're using the same techniques down at the Linux core. So process and network isolation, C groups, seccomp, which lets us limit some of the surface area of the OS kernel that these processes see. And then, of course, off-the-shelf language runtimes that we couple into those images and place in a chroot jail. And our whole goal at this level of the system, to be perfectly honest, is to minimize innovation. Right? We want to use things that other people have developed. We want to, when there's a security enhancement, for example, to something like the low-level container technology in Linux, we want to be able to get that quickly and not have had to do too much innovation on our own. So we had some security policies in here. There are a few things we do at that level, but in general, we try hard not to do a lot of innovation there. What we do innovate is at the next level up. And I used to say jokingly that we've built the world's biggest bin packing algorithm, only now I'm not so sure it's a joke any longer. It's essentially the core of what Lambda does is a high-speed, highly distributed work routing and placement engine. So kind of work comes in the front door, and then we basically have about a millisecond and a half to land that work in the typical warm case on a container that's been spun up and is ready to accept it, subject to a whole variety of policies. Security policies most importantly, of course, but then also economic and efficiency policies. And this is kind of exactly the sort of thing that we're trying to save customers from having to do. Because it's challenging managing a fleet kind of at that size and that scale, and having to make sure that that work occupies as few of those instances as possible. So there's a huge kind of server packing problem here, right? And that's kind of the core of what we try to spend our time optimizing. It's also, frankly, where kind of my economics as a business are mostly driven. And then to make that work, there's kind of the one-third piece here, which is what I call the predictive capacity management. That work has to land on something that's prepared to take it. And so kind of internal to Lambda is this thing which is like a language runtime as a service. It's basically firing up and warming up not just the operating system, but the language runtimes, getting all of that ready to go, making sure it's hooked up, appropriately configured, and then kind of plops that out so I can start landing work for the right people and the right accounts at the right times on top of it. And making sure that that thing predicts accurately is kind of key, because if you have too few, obviously those requests don't get answered. You get too many, and then your economics go upside down. And then Gateway's a little simpler. Gateway's, you can think of kind of as a Swagger interpreter. It's a reverse proxy, and then it's taking that API description and essentially executing that for multi-tenanted clients in a highly sharded fashion. And the two of these plug together in sort of the obvious way then. Okay. Kind of background material on what serverless is, a bunch of description about kind of Lambda and Gateway. Now let's talk about what you can do with all of this. So how do you take the Lego pieces and build something interesting out of them? Particularly, how can you build something which looks like a serverless solution end to end, kind of design patterns for the modern cloud? Well, you already saw one of these. So let's start with the one that we demoed here. So serverless web apps. So as I mentioned, this is dynamic content getting served up through Lambda, fronted by API Gateway, and we chose in that demo to store it in DynamoDB, which kind of plays in nicely with the serverless solution here, since you don't have to worry about actually going and landing that somewhere as a piece of infrastructure. And then the static web content being served out of S3 here. And as I mentioned, we did a kind of a heavy client, thin server. We could just as easily have done dynamic server, kind of thin client. And then you get a couple of choices about how you architect this. So some people do function per endpoint or per route in the URI. Some people prefer to kind of have one function which is mastering all of that. So a few different patterns there, depending partly on your preferences and of course partly on how you like to style your JavaScript client. Now closely associated with that one, because it's fairly similar in its architecture, scalable backends for mobile apps and IoT devices. So kind of similar here, you can pick Lambda and Dynamo sort of serving that same sort of architectural role on the back end, and then connect it either through a mobile client, possibly with some extra authorization help. We've got a service called Cognito that does that. Or if you're using an IoT device, through something like the AWS IoT service, which is the thing that'll chat MQTT to your individual devices. But otherwise, a similar kind of architectural pattern, and giving you similar kinds of capability in terms of scalability and fault tolerance without having to actually encode a bunch of those. So at this point I want to kind of take a quick pause and talk a little bit about kind of that. How do we save that complexity, right? Mobile developers being a great illustration of where we want to make sure they can spend their energy on the client side, not on the server side. And so it's illustrative to pick something that's a mature technology today like Java. If you look around the planet, there are maybe dozens, small hundreds of developers who spend their professional lives writing JVM technologies like Hotspot, right? Relatively few on the entire planet. There's a somewhat larger ecosystem of people building compilers and tools and kind of Java-related frameworks and technologies in service of ultimately what are probably millions of Java developers who are operating professionally. And I'd argue in the fullness of time, we're going to see that same kind of pyramid occur for Lambda functions and similar kind of tech, right? Where the function hosting is going to be done by a small number of cloud providers who've got kind of the capital-intensive capability to go do that. Supported by event and app ecosystems, and we'll take a look at some third parties who are doing that today in a bit here. And then ultimately in support of a large number of developers who are bringing the applications to that platform without having to spend the energy to develop the underlying complexity. Okay, so we talked a little bit about kind of the mobile and web, kind of the back-end domain. Let's chat a little bit now about design patterns for events and event handlers. So I've already mentioned one of the most common ones of these, and this is today probably the, along with Dynamo, kind of are the two most popular ones that I see running on top of Lambda. S3 is a really easy place and a natural part of kind of the storage workflow for enterprises and startups to kind of put images, documents, all kinds of objects. And typically, when they do that, there's some kind of workflow they want to kick off. So images is a perfect example. You upload an image, you want to make some thumbnails of the image, maybe you want to replace the original. You might want to put objects up, compress the objects, and then delete the original. Lots of kind of things that kind of fall into that kind of thematic route. And Lambda makes it really easy to do that simply by hooking up a function to that particular bucket. Now, why does this work really well? Like, what's kind of going on there under the covers? After all, having your code call something like Dynamo or S3 isn't particularly complicated. What makes it interesting is the callback, the ability for these services to call back into Lambda. And then when you couple those two things together, you can essentially create behavioral abstraction. Not entirely unlike a method sitting on an object, you can now take something which has internal state and some clear ways by which it gets manipulated. In fact, what's interesting about something like a table is that you can change its behavior without the user of the table necessarily knowing. So somebody is putting zip codes into a DynamoDB table, you can attach a Lambda function which canonicalizes the zip codes, makes sure they're all in 9 digits, kicks back any erroneous ones, cleans them up, for example, and the user of that table never had to know that you have attached that functionality. Of course, you can also take this box, kind of put a bow on it, and stick an API out in front, and then call it a brand new service doing something else. All right, so one more example of kind of the design pattern type for events here. Lots of people these days are moving into kind of this real-time streaming, right? Kind of another sort of industry-shaping paradigm that's kind of rolling out concurrently with some of the serverless ones. And the reason's very obvious, right? I mean, like who wants to sit around and wait for their computation to finish? Certainly, like those business guys are always yelling in your ear to give them the reports faster. So what if we could take all of that information, whether it's like data coming in from an IoT device or clickstream data, and pump it through the stream and then act on it right away? So to do this with Lambda, we hook it up to another AWS service called Kinesis, a real-time streaming engine, which lets us put data in and then hook all these Lambda functions up. And then what's going on there is that Kinesis has essentially this unit of parallelization called a shard, right? So each shard is processing an in-stream ordered array of information. Each shard gets a Lambda function, and so you get to control the parallelism in Lambda simply by setting the shard count in Kinesis. And then at that point, the Lambda functions can aggregate, transform, send things off to Dynamo or Redshift or wherever it is you want to send them. So this is kind of a good point to step back and talk about, how work arrives there, because now we've kind of covered a few different types. Synchronous calls, the most obvious, mobile app calls into a function, kind of standard RPC, waits for a response. Async, that's like the S3 pattern. So you put an object to a bucket, and then behind the scenes, S3 will go ahead and call Lambda and tell Lambda about what just happened, typically on the order of a few hundred milliseconds. Kinesis and Dynamo change streams work by polling. Think of Lambda functions kind of attached as a feeder to each one of those shards, chewing through the data as those shards progress and get new information built into them. Schedules and cron, fairly straightforward. And then, events here are really just the things that are being transmitted in those pipes between the two services. Again, trivial programming model in the sense that it's just JSON. What isn't trivial here, and is kind of this interesting thing that goes on behind the scenes, is the operational complexity. So let's say you go from putting maybe one object every minute in S3 to putting 10,000 objects every second. All of a sudden, behind the scenes in some data center or somewhere, a massive amount of machinery has to start spinning up. And that pipe between S3 and Lambda has to be able to account for that impedance matching, essentially, and with the kind of a resolution of a second or two responsiveness. And that's the kind of thing that's really difficult to do as a client. Inserting yourself into that mix, particularly inserting your application into that mix, is hard because you've got to be able to respond with a scalable system in that same way. Pulling these events behind the scenes allows those two services to chat directly with each other. And when something goes wrong, allows those two teams to chat directly with each other. Not that that happens. All right, last design pattern here. A lot we could talk about, but I want to share one final one. And I want to broaden out for this one beyond, what can you do with different Lego blocks inside of AWS, and talk about some brand new ecosystems that are getting developed by, in one case, other parts of Amazon, and in another case, by a third party. So we did this example. It's actually up on the AWS Compute blog. You can go see the code that was involved in making it work. What I wanted to do was be able to talk to my Amazon Echo and say, Alexa, tell Slack, and then insert some message that I wanted to send to my team, and then have Alexa speak back, the response from my team by listening on the Slack channel. And this is a really interesting one because it actually takes not just one, but two different ecosystems and gives them a serverless hosting capability. And this is probably the most interesting design pattern of all. Because from Slack's perspective, they really want to get developers writing applications in the fastest way, in the easiest way to kind of grow their ecosystem. The Alexa guys have the same desire. And here's where serverless really has an amazing effect, because the folks who are doing that don't necessarily want to think about infrastructure. They want to think about just building an Alexa skills kit or responding with a serverless bot to a Slack channel. Okay, let's talk about a few other kind of points here in, about how we kind of connect this into sort of the broader ecosystem of the enterprise. This is sort of a kind of a topology diagram for API gateway. I wanted to put this up to illustrate how you would plug in kind of a SaaS backend. So let's suppose that you've got this API, but you also need to reach out to your CRM or ERP solutions. So the gateway can call Lambda, but it can also call any other endpoint. So you can use that to connect to sort of the other systems by which you establish and retrieve sort of your enterprise business data. You can also fold that through a Lambda function if you want to shape that data, either coming or going. So it's easy to build transforms and aggregations by putting the two together. You can also use Lambda as a custom auth experience. So if you've got something, say, where you need to reach into an internal system, typically within a VPC this would be, or even back through a VPN, you can establish the credentials, the credibility, if you will, of somebody who's attempting to use the API. As I mentioned, we've been excited by not just the number of customers who are using this, but also interestingly by the breadth of industry sectors who've begun using serverless already. And I'll be perfectly honest, I've been as shocked as anyone at the sort of the rapidity with which the adoption has gone here. We always expected startups would love this, but it's been shocking to see the number of enterprises who are kind of moving quickly into this domain. But they get the same kinds of advantages, and they can kind of see where that trend line is going and want the same kinds of outcomes for their own businesses. So we see folks like Localytics who do the kinesis pattern that I showed you earlier, processing analytics data at massive scale. We see folks like AdRoll who are doing the S3 pattern that we talked about earlier, and doing sort of large-scale image and media conversion and manipulation. Major League Baseball, which is doing interesting kind of real-time game statistics and then outreach to their mobile devices. So all kinds of amazing and very, very varied and heterogeneous workflows. And then finally, a couple of sort of logistics here. I'd be remiss if I didn't mention anything about kind of pricing. You saw sort of the durations that we could pick and that were reported in the demo. Lambda charges 20 cents per million requests, but it's priced by individual requests, so you can make as few as one or as many as billions a day if you like. And then there's a free tier, which lets you do 1 million requests and 400,000 gigabyte seconds of compute every month, every customer, forever. And that means that lots of people can actually do all of their development work, and for small companies can even do some of their production application hosting directly inside of the system. And of course, the coolest thing about this of all is the never pay for idle piece, because what you don't pay for here, now or ever, are the servers that are sitting around not doing anything for you. As of last week, we actually have matched in IoT to sort of all of our regions. We now have East and West Coast in the US, 2 European regions, and Tokyo. So have that coverage for IoT, Gateway, and Lambda in all of those regions. All right, final part, how do you join the serverless revolution? So those of you who are product managers or business analysts, I'd invite you to go check out the website. We have a lot more detail around those customer stories. It's interesting to see what those businesses are doing and why they've made this decision and elected to kind of go down the serverless route. If you're a developer, I'd encourage you to kind of go recreate that demo that I just did. Go to the Lambda console, create a function, and run it. You saw how easy it was to get started there. A bunch of blueprints you can choose to kind of begin your journey on this. And it doesn't take long to kind of develop some expertise, given that simplicity, so you can very quickly add HTTP endpoints to build the kind of serverless web experience you saw me do, or get going with something like the Alexa Skills Kit to produce, an Amazon Echo app, or attach this to something like a mobile backend or a third-party system. And then, of course, we can all consign our DevOps tools to the dustbin of history along with punch cards. Thanks so much, and if we have some time here, we can take a few questions as well. Yeah.
What is the next language, and will we see Golang support in the future?
Yeah, so I'll give you two answers on that one. Enterprises always tell me they want either C# or Ruby, and from everybody else, I always hear Go. So C# and Go are at the top of our list. I can tell you that much. We're actively pursuing both of those. Getting Node out the door was obviously a short-term priority. As is making sure we have enough Python support. So, making sure all of our existing languages are already well supported. Yes?
Can you talk about what happens when the 10,000 objects come into S3, and then are there auto-scaling policies around Lambda?
Yeah, so what happens when 10,000 objects hit S3 with a function attached, and is there an auto-scaling policy? So first of all, Lambda's designed to kind of respond to that automatically. So what we'll do in that case is, we will audit behind the scenes. We're doing something not entirely unlike auto-scaling in the sense that we're bringing a whole bunch of machines online. However, we're attempting to do it much faster than autoscaler would do, because that typically provisions and boots new instances for you, right? And we're trying to get S3 events to process within the space of a few 100,000 milliseconds. So what we're going to do in this case is we'll take some of those machines that we've warmed up, essentially. Let's think of it as a warming pool. We'll pull those machines over to the account in question, and then we'll start processing the code that is hooked up to that particular S3 bucket. And they'll
contact you to warm Lambda?
No, you don't have to contact us to warm, but what we do is we put safety throttles on accounts to make sure people aren't doing something they didn't mean to do, for example, with runaway recursive code and so forth. So if you want to do something at that level, you typically contact customer service and say, yep, I'm good, I'm good to go, I need a higher throttle limit, and then we'll turn that up, and then you can do exactly what you described. Yes, sir?
Is there a solution for long-running jobs that are not quite so easy parallelized?
Yeah. So the question was, is there a solution for long-running jobs? This is probably our most, kind of the most common request, and one of the reasons we took it up from a minute to 5 minutes. So in the short term, what most people do is they'll go fire up ECS or EC2 in the background, and they'll kind of run something. They'll basically use Lambda to choreograph a longer running task, but they'll handle the event manipulation part and any kind of short-term dispatch that they can in Lambda. And over the long haul, no pun intended, our intent there is to be able to give people longer running jobs as well. It starts to suggest that you want to be able to check on the status of those jobs and so forth. So it's a little more than just turning the duration number up as we go beyond 5 minutes.
So longer durations is on the roadmap?
Longer durations is definitely on the roadmap. Along with it starts to beg the question of things like, well, then could I start to define it with a Docker image or something else? And so we're trying to find the right shape to describe a job that can run, say, for 5 hours at a time instead of 5 minutes at a time. Yes?
So you mentioned that you would probably go up and down based on how many resources you want to dedicate to. You know how you mentioned the dial that you go up and down on how many resources? Do you have any transparent way of looking at how many cores, memory, disk was used as part of the completion of the job?
Yeah, so we've tried not to define it, and this is one of the reasons it's expressed in memory terms, right, is we've tried not to define it in terms of cores because over time, as obviously as computer architectures change and instance types change, we'll end up running it on different machines, probably machines that grow more cores over time. So today, depending on the number you set, you typically are getting 1 or 2 cores depending on the machine. We try to keep the, and sort of the consistency part of this, like we try to keep the amount of compute power that you get for a given level stable over time. So that dial is intended to keep meaning the same thing as much as we can have it be so. Now that said, of course, like, so machines tend to get faster over time, so it becomes a little tricky to do that. But that's you can kind of like, you can obviously do some steps to check, yourself to see how many cores you're running on a given machine. We try not to put that in kind of the public statement of the behavior for precisely this reason, right? Because technology will advance over time. Yes?
To what degree is this particular customer's code running on particular hardware? I mean, if you go to that question, it's not clear to me that they would be on particular hardware. And if they're not, what's the isolation between my code and next guy's code?
Yeah, so we do not yet fully trust, let me say, containers are great. They continue to evolve and improve. They're a wonderful thing. We do not yet trust them for cross-customer isolation. And so we use a combination of hypervisors, containers, and then our own proprietary security techniques to ensure that there's no crosstalk between accounts. We'll be slightly more trusting, say, within instances of a single function that you happen to be running because they all belong to you and we believe that they will not be attempting to harm one another. So we'll modulate the security policy, depending on factors like that. Yes?
So let's say I'm using Python as a C library. How do I make sure that library is there for me?
So you package up the code and give it to us as a zip, including all of the binary dependencies. So when you bring it, when you send it to us, you send it inclusive of whatever library you've created or defined there.
So compiled for a specific implementation then?
Yeah, so basically we run on Amazon Linux, we publish the version that we do. You essentially would compile your code for Amazon Linux, right? And then you would send it to us in kind of in zipped form. Yes?
Talk about the different power levels. Generally speaking, you end up paying for the power level you request, not the power level you actually use. Is that true?
You pay for the time that you spend using the power level that you request. Yep. So this is one way in which you can exceed, in some sense, you can ask for something and then not actually use it in terms of the full capacity, but not for any additional time. Yeah, all the way in the back.
We use Kinesilite on local development boxes before we use real Kinesis. Is there a similar way to run Lambdas locally and kind of get that architecture running like in a Docker VM? Or are developers writing Lambdas sort of pushing their most recent attempts up to AWS every time? What's the development cycle there?
I could only hear part of that, but it sounded like you're asking, is there local testing?
Yes.
Yeah, and so there are a couple of easy answers there. There's some folks like Serverless.com who've built some test infrastructure. So there generally are open source solutions for Node and Python. If you're a Java developer, we have JUnit testing support inside of the Eclipse plugin that you can download, and then you can also pull that out and run it on the command line. So that's kind of the easiest Java solution. And if you're a Visual Studio lover, then you can run test runner code inside of Visual Studio, same kind of solution for Node.js.
Is there a way to plug in locally to Kinesilite?
Plug in locally to?
Kinesilite. It's a Node.js package that simulates Kinesis, and you can pull from it with KCL.
Got it. I have not seen that done yet, but that's a great. I'll take that one as a follow-up. And it's that and Dynamo are two of the most popular things people ask for kind of local connectivity on. So it'd be really interesting to see us kind of spin up some of that easy test infrastructure. And then just in sort of the interest of being respectful to the next folks who's in the room, how about I'll call it here, but I'll be around outside if people have additional questions. So happy to take more.